Space, the final frontier. A boundless expanse that stretches far beyond what our eyes can see or our minds can grasp. It is not just distance that defines it, but mystery. Deep, ancient mystery that has stirred the human soul since the first time we looked up at the stars. We have mapped constellations, named planets, and traced the paths of comets. Yet the vast majority of the universe remains untouched by our instruments and unknown to our understanding. Every night, sky is a silent invitation to ask, what lies beyond? From the earliest myths to the most advanced telescopes, humanity has been drawn to the heavens not only to seek answers, but to find meaning. The cosmos is more than just a stage for galaxies and stars. It is a mirror reflecting our curiosity, our fragility, and our longing for connection. As we embark on this journey through space and time, we will not only explore the birth and fate of the universe, but confront the limits of perception itself. This is a story about where we are, how we got here, and where the universe might be heading. Perhaps even how it might end. When we speak of the universe, we often imagine it as one vast, unified whole. But in truth, we can only speak with certainty about a fraction of it, a region known as the observable universe. This is the part of the cosmos from which light has had time to reach us since the beginning of space and time. Every star we see in the sky, every distant galaxy photographed by our telescopes, lies within this boundary. Beyond it, a veil of silence and darkness, where no signal has ever arrived. Not because there is nothing there, but because light, the great messenger of the cosmos, simply has not yet arrived. Light is fast. Indeed, it is the fastest thing we know. But even light takes time to travel. From the surface of the sun to the Earth, it takes about 8 minutes. From the closest star beyond our solar system, it takes over 4 years. When we gaze at distant galaxies, we are not seeing them as they are now, but as they were millions or even billions of years ago. To look into deep space is to look into deep time. Our night sky is not a snapshot, but a layered tapestry of the past, each star a relic from a different moment in the history of the universe. The age of the universe is estimated to be around 13.8 billion years. So, one might assume that the farthest thing we can see would lie at a distance of 13.8 billion light-years. But that is not the case. Because the universe has been expanding ever since its beginning, the regions from which the earliest light was emitted have moved farther away. Today, the edge of the observable universe lies roughly 46.5 billion light-years from us in every direction. This is not because light traveled that far, but because the very fabric of space has stretched during the journey. It may seem paradoxical. How can we see something that lies farther away than the universe is old? The key lies in cosmic expansion. Space itself is not static. It is growing. Imagine light as a traveler moving along a rubber sheet. As the sheet stretches, the traveler is carried farther from the starting point, even though the steps taken remain the same. In this way, the light we now detect has come from regions that are now far more distant than they were when the light first began its journey toward us. This boundary, the radius of our visible universe, is known as the particle horizon. It is the maximum distance from which light, emitted in the past, could have reached us by now. It forms an invisible sphere centered on Earth, surrounding us like a cosmic shell. But this horizon is not the limit of the universe itself. It is simply the limit of what we can currently see. Beyond it, the cosmos may stretch infinitely, filled with galaxies that have never and may never send their light our way. These distant regions lie forever beyond our reach, not in space, but in time. There is another type of limit known as the event horizon of the universe. While the particle horizon tells us how far we can see into the past, the event horizon defines the boundary beyond which any light emitted now will never be able to reach us in the future. Because of the universe's accelerating expansion, some galaxies are moving away from us faster than the speed of light, not because they are breaking any laws, but because space itself is expanding. This makes them unreachable, not just in practice, but in principle. Beyond this event horizon, objects may continue to exist, but for all intents and purposes, they have vanished from our cosmos. Even if we were to send a message today, a pulse of light aimed at a distant galaxy beyond the event horizon, it would never arrive. The galaxy would recede faster than the signal could travel. As time marches forward, more and more of the universe will cross this horizon, disappearing from view forever. Our observable bubble will remain, but the outside world will fade into the unreachable dark. Yet, the universe is not uniform. It is filled with stars, gas, dust, and entire galaxies. The light from many of these objects has not yet reached us, but someday it will. The observable universe is constantly growing, not because the universe is changing, but because light from ever more distant regions is finally arriving. As our telescopes become more sensitive, we see further, not by moving outward, but by letting the past come to us, photon by photon, like ripples on a vast ancient sea. Still, there are places we may never see, no matter how patient we are or how advanced our instruments become. Some regions of space are simply too far, too fast. The Hubble horizon marks a theoretical limit, where the expansion of space carries galaxies away at the speed of light. Anything beyond this limit is receding faster than light can travel. No signal can bridge the gap. These cosmic boundaries are not physical walls, but consequences of space-time itself, woven into the geometry of reality. To grasp the scale of the observable universe is to confront the limits of perception. What we call the universe is, in truth, a personal map of what light has brought to us since the dawn of time. Beyond our cosmic horizon, entire galaxies may be forming, colliding, or dying, and we would never know. Our instruments may improve, and our understanding may deepen, but we remain bounded by light. Our knowledge of the universe is shaped not only by what exists, but by what light has chosen or been allowed to show us. Long before the first galaxies formed, before stars illuminated the sky, the universe was a seething ocean of particles and radiation, hot, dense, and opaque. In those early moments, photons, particles of light, could not travel freely. They collided constantly with electrons, bouncing from one interaction to another, imprisoned in the fog of the infant cosmos. There was no transparency, no view across the void. The universe was glowing, but blind. As the universe expanded, it began to cool. After about 380,000 years, a threshold was crossed. Temperatures dropped enough for electrons and protons to combine, forming the first stable hydrogen atoms. With this transformation, the fog lifted. Photons were finally released from their endless collisions and allowed to stream freely across space. This moment is known as recombination, and it marks the birth of light's long journey across the cosmos. That ancient light still exists today. It fills every corner of space and continues to reach us from all directions. But it has changed. Over billions of years, the expansion of the universe has stretched the wavelengths of those primordial photons, shifting them into the microwave region of the electromagnetic spectrum. What was once a bright and fiery glow has become a soft, invisible whisper, the cosmic microwave background. First detected in the 20th century by accident, this background radiation is one of the most profound discoveries in cosmology. It is not light from stars or galaxies. It is the afterglow of creation itself. When astronomers Arno Penzias and Robert Wilson recorded a faint, uniform signal coming from every direction in the sky, they had unknowingly tuned in to the light of the early universe, still echoing after nearly 14 billion years. This radiation is incredibly faint, corresponding to a temperature just a few degrees above absolute zero. It cannot be seen with the naked eye, but with the right instruments, it paints a map of the universe's childhood. It is not entirely smooth. Tiny fluctuations in temperature, fractions of a degree, scatter across its surface. These small variations are the seeds from which galaxies, stars, and planets would eventually grow. Imagine looking at a photograph taken when the universe was still an infant, a snapshot that captures not only its temperature, but its structure and potential. The blue and orange patches we see in cosmic microwave background maps correspond to areas of slightly different density. These are the fingerprints of matter in motion, imprinted at the dawn of time. From them, scientists have traced the evolution of cosmic structures, from faint ripples to vast galaxies. The importance of this background radiation cannot be overstated. It is the closest thing we have to direct evidence of the Big Bang. Its uniformity supports the idea that the universe began in a single, hot, dense state. Its tiny variations support models of inflation, the brief period of hyper-rapid expansion that likely occurred in the first fractions of a second. And its detailed structure allows us to estimate the age, composition, and curvature of the cosmos with extraordinary precision. One of the most remarkable insights provided by the cosmic microwave background is the discovery of the universe's flatness. According to general relativity, the shape of space is influenced by the amount of matter and energy it contains. The patterns observed in this background radiation suggest that the universe is flat on large scales, not curved like a sphere, nor open like a saddle. This flatness is both a clue and a constraint for modern cosmological theories. But the cosmic microwave background tells us more than just what the universe is. It hints at what it will become. From its patterns, scientists have inferred the existence of dark matter and dark energy, the unseen forces that govern the cosmos. Dark matter helps form galaxies, while dark energy drives the universe's expansion. The balance between them determines the future trajectory of space itself, whether it will expand forever, slow to a halt, or collapse inward again. Thus, in the faint glow of ancient light, we find a story both primal and profound. A silent witness to everything that has ever been, the cosmic microwave background is the echo of the universe's awakening. It links us to a time when atoms were just beginning to form and light was just beginning to travel. Every photon that reaches us from that era is a message from the past, a whisper across billions of years, telling us how everything began. Light has long been our most faithful guide through the cosmos. It carries ancient stories across impossible distances and illuminates corners of the universe we could never reach by any other means. But light is not perfect. It can be blocked, absorbed, bent, and delayed. Worse yet, it is limited by time. There are places in the universe so far, so hidden, that no photon will ever reach us. To explore beyond these cosmic limits, we must turn to more elusive messengers, particles and waves that move in silence through the fabric of the universe itself. Enter the neutrino. This ghostly particle is almost without mass, nearly impossible to detect, and yet it is everywhere. Born in the heart of stars, in violent supernovae, and in the earliest moments of the universe, neutrinos pass through matter as if it were not there. Every second, trillions of them stream through your body, unhindered. Because neutrinos so rarely interact with other particles, they can journey across the vast universe without losing energy or being deflected. They are, in a way, nature's perfect time travelers. Neutrinos can reach us from places that light never could. From the edge of a collapsing star or the depths of a black hole's formation, they escape unharmed while photons remain trapped. Studying neutrinos allows us to peer into the darkest and most violent corners of the cosmos. But detecting them is a monumental challenge. Only the most sensitive instruments, often buried deep underground or beneath layers of ice, can register their fleeting presence. Even so, each detection is a window into events billions of light-years away. But neutrinos are not alone. There is another silent messenger, one that does not move through space, but instead is a ripple in space itself, the gravitational wave. First predicted by Albert Einstein, gravitational waves are distortions in the very fabric of space and time caused by massive objects accelerating, like black holes merging or neutron stars colliding. These waves travel outward at the speed of light, carrying information not just about where something happened, but how space-time was bent in the process. In 2016, scientists detected gravitational waves for the first time. Two black holes, over 1 billion light-years away, spiraled into one another and shook the universe. That ripple reached Earth, stretching and squeezing space ever so slightly, less than the width of a proton. And yet, from that nearly invisible motion, a new era of astronomy began. Gravitational waves have no need for light. They cannot be blocked by dust or gas. They reach us from places no telescope could ever see. Together, neutrinos and gravitational waves form a new language of the cosmos. They allow us to go beyond the visible, to detect events in darkness, to hear the echoes of creation, to witness collisions and cataclysms no beam of light could ever escape. They do not replace light, they expand it. Like learning to see with new eyes, or to listen with new ears, these phenomena offer a deeper understanding of a universe once thought unreachable beyond the edge of sight. The universe is not silent. It sings in gravitational tremors and whispers in streams of neutrinos. These subtle signals reveal truths buried beneath the noise of stars and galaxies. As our instruments grow more refined, we begin to tune into this deeper harmony, one where time bends, space ripples, and the past arrives not only as light, but as distortion and resonance. To understand what lies beyond our observable horizon, we must not just look, we must listen. And this is only the beginning. Future observatories may one day detect neutrinos from the birth of the universe itself, or gravitational waves from before light could travel. Each wave and particle is a letter in a cosmic language, and we are just learning to read. If light defines the surface of what we know, then neutrinos and gravitational waves may unveil what lies underneath. A new universe waits in the silence, and we are learning, at last, how to hear it. From the moment of the Big Bang, the universe has been expanding. Not like an explosion through space, but rather, space itself has been stretching, growing larger in all directions, carrying galaxies with it. This expansion is not something we can see directly with the naked eye, but its effects are imprinted in the very fabric of the cosmos. Distant galaxies appear to be receding from us, their light stretched into longer, redder wavelengths, a phenomenon known as redshift. The farther a galaxy is, the faster it seems to move away, This observation, first made in the early 20th century by Edwin Hubble, led to a profound realization. The universe is not static. It is dynamic, in motion, and changing with time. The space between galaxies is growing, not because the galaxies themselves are moving through space, but because space itself is expanding between them. This means that over vast scales, every point in the universe is getting farther from every other point, not because they are moving, but because the stage on which they sit is stretching. At first, scientists believed that gravity would eventually slow this expansion, perhaps even reverse it. But in the late 20th century, observations of distant supernovae revealed something astonishing. The expansion of the universe is not slowing down, it is speeding up. A mysterious force, known only as dark energy, appears to be pushing the universe outward, accelerating its growth. The farther we look, the faster galaxies flee. The cosmos is not just expanding, it is accelerating into the unknown. This accelerating expansion has profound consequences. First, it means that more and more of the universe will eventually slip beyond our cosmic horizon. Galaxies that are visible today will someday vanish from view, not because they cease to exist, but because their light will never reach us again. They will recede faster than light can travel, carried away by the very expansion of space. What we can see will shrink, not in size, but in content. The universe will appear emptier, lonelier, and colder with time. The expansion also affects how we understand the age and fate of the universe. Because space is stretching, the light from distant objects takes longer to reach us, and what we see is not just far away, but also ancient. We look at galaxies not as they are, but as they once were. And because the universe is accelerating, the age-distance relationship becomes more complex. It challenges our perception of time itself, of what is now, what was then, and what can ever be known. There are multiple horizons in cosmology, shaped by expansion. The particle horizon marks the limit of what we can currently observe, the distance from which light has had time to reach us. The event horizon, however, defines the ultimate limit, beyond which even light emitted today will never arrive. Finally, there is the Hubble horizon, the threshold beyond which space is expanding faster than light. These horizons are not walls, but boundaries of knowledge, defined by the physics of light, time, and space. The growth of these horizons means that the observable universe continues to change. Over time, we gain access to light from more distant regions, but simultaneously, the event horizon draws inward. The universe is pulling away from itself, one part becoming invisible to another. One day, only the closest galaxies, gravitationally bound to us, will remain visible. The cosmic tapestry will fade, one thread at a time, until all that is left is our local group, trapped in an island of light, adrift in an infinite sea of silence. This expanding emptiness poses challenges not only to our observations, but to the very future of science. As more of the universe disappears from view, future civilizations may see only a handful of galaxies and stars. Without the cosmic microwave background or evidence of distant expansion, they might never know the universe had a beginning at all. Our current age, then, may be uniquely privileged, a moment when the universe is still readable, when its history is still written in light. Yet, not all is lost. The expansion may one day slow. Some theories suggest that the balance between dark energy and dark matter could shift. If gravity regains control, the universe might stop expanding and begin to contract, collapsing inward in a dramatic reversal called the Big Crunch. Or perhaps the expansion will continue forever, ending in a cold, dark, and empty void, a scenario known as heat death. The destiny of the cosmos is written in forces we are only beginning to understand. So the universe expands, not just in distance, but in mystery. Every second, every breath, every flicker of light adds to a story that is moving outward, away from its origin. We are part of this expansion, not separate from it. Our atoms, our thoughts, our questions are all unfolding on a fabric that grows larger with each passing moment. In the quiet pull of space, in the stretch of starlight, the universe reveals itself not as a place, but as a process that carries us forward into the unknown. As we gaze into the night sky, we often wonder not only about the past of the universe, but its future. What lies ahead for our planet, our star, and the galaxies that drift through the cosmic sea? The near future of the universe, spanning from a few thousand years to several billion, will witness both profound beauty and irreversible change. The story begins not with distant galaxies or ancient black holes, but here, on Earth, where our species has begun to leave its mark on the planet's evolution. By the year 2500, Earth may no longer resemble the world we know. The planet's magnetic field, which shields us from cosmic radiation, is slowly shifting. At some point, the magnetic poles will reverse, a process that has occurred many times before, but not in human history. During this transition, satellites may malfunction, navigation systems may fail, and radiation from solar storms may reach the surface more easily. It will not be the end, but it will be a reminder of how fragile our technological world is. Not long after, Earth will begin to feel the heat of its aging star. The sun, though stable for now, is gradually growing brighter. Within the next 1 billion years, its luminosity will increase by around 10%. That small change will have devastating consequences. As temperatures rise, photosynthesis will begin to fail. Plants will wither, oxygen levels will fall, and the atmosphere will grow hostile to life as we know it. The blue and green world that once teemed with life will begin to fade. By the time Earth is 1.5 billion years older, the oceans will start to evaporate. Water, The very source of life will vanish into the sky and be lost to space. What remains will be a scorched and barren landscape, a memory of a planet that once sang with birdsong and bloomed with color. Life may retreat underground or vanish entirely. The Earth, once a cradle of consciousness, will become silent. Fast forward to the 5th billionth year from now, and the Sun will enter its final phase. No longer able to fuse hydrogen in its core, it will swell into a red giant. Its surface will expand, engulfing the orbits of Mercury and Venus, and perhaps Earth as well. Even if Earth escapes direct destruction, its surface will be burned beyond recognition. The Sun's transformation will be slow and dramatic, a cosmic reminder that nothing, not even stars, lasts forever. Eventually, the Sun will shed its outer layers into space, forming a glowing planetary nebula. What remains will be the Sun's core, a dense, hot white dwarf. No longer a furnace of fusion, it will slowly cool over billions of years, fading into darkness. The once brilliant star that gave Earth its light and warmth will become a cold ember, lost among the stars. While our solar system ages, so too will our galaxy continue its majestic drift through space. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. This titanic event will not be a violent crash, but rather a slow dance of gravity, where stars pass one another in silence. Over millions of years, the two galaxies will merge, forming a new, larger galaxy, perhaps an elliptical giant. Stars will be born, others will die, and the structure of the cosmos will shift once more. Even as the galaxies merge, most stars will survive the transition, but the structure of the night sky will be forever changed. Constellations will distort, the sky will glow with new clusters of stars, and the solar system may find itself in a very different corner of this new galactic home. Humanity, if it still exists, may witness this event not from Earth, but from distant worlds, having spread across the stars or evolved beyond physical form. These changes, vast in time yet inevitable, remind us that we live in a moment. The conditions that sustain us are temporary. The warmth of the sun, the air we breathe, the oceans that cradle our continents, none will last forever. The universe does not rush, but it does not stop. Every second, the clock ticks forward. The near future of the universe is already unfolding, and we are part of its story. And so we look ahead, not with fear, but with reverence. For every end is a beginning, and every transformation is an opportunity to wonder. Stars are born and die, galaxies collide and reform, worlds vanish and others emerge. We are witnesses to a universe that never stands still, a cosmos in motion, where even the sun will someday set for the final time. Yet in that sunset lies a deeper truth, that nothing is permanent, and therefore, everything is precious. There will come a time in the distant future when the last stars will burn out. One by one, these brilliant furnaces of fusion will exhaust their fuel and go dark. Without stars, the universe will no longer shine. It will become a quiet, empty theater, stripped of its radiant actors. The night sky, once a canvas of light and wonder, will fall into a permanent twilight. This is what physicists call the end of starlight, a moment when the universe begins to fade into shadow. The death of light is not sudden. It arrives gradually, over countless billions of years. The most massive stars vanish first, going out in explosions of incredible energy. Smaller stars, like our Sun, endure longer, quietly fading into white dwarfs. But even these remnants will cool, dim, and eventually disappear. The universe will be filled with cold, dark cinders, black dwarfs that no longer emit light. They will drift silently through space, invisible and forgotten. And yet, darkness is not the end. Even after the last photon fades, the universe will continue to change. Deep within every atom lies a particle known as the proton. It is one of the fundamental building blocks of matter, present in every star, every planet, every cell. For a long time, protons were thought to be perfectly stable. But some theories now suggest that even they are not eternal. Given enough time, protons may begin to decay. Proton decay is a concept born in the realm of high-energy physics. According to certain grand unification theories, protons are not truly immortal. Instead, they may slowly break apart into lighter particles, neutrinos, photons, and other subatomic fragments. This process would happen over unimaginably long timescales, perhaps 1,000,000 trillion years. But once it begins, it signals something profound: the unraveling of matter itself. If protons decay, then everything built from atoms will eventually fall apart. Planets will disintegrate. White dwarfs and neutron stars will crumble. Even the black dwarfs that once held the last heat of the cosmos will vanish into radiation and dust. The universe will be stripped of all structure. No stars, no planets, no atoms. Just a thin, cold fog of particles drifting endlessly through expanding space. This era, known as the Degenerate Era, marks the slow but certain dismantling of all physical form. It is not an explosion or a collapse, but a quiet erasure. The universe, once bursting with light and complexity, becomes a ghost of its former self, a place where time still flows, but change has nearly ceased. The death of light is followed by the death of matter, and both together lead to a universe of stillness. It is tempting to see this future as tragic, but in another sense, it is a story of transformation. Just as stars were born from clouds of gas and planets from stardust, the decay of matter is part of a cycle, one that spans a timeline beyond imagination. From the fire of the Big Bang to the silence of the far future, the universe evolves. And though its final chapters may be quiet, they are no less profound. In the fading echoes of light and the whisper of vanishing protons, the cosmos completes its long, graceful descent into darkness. When the last stars have faded and the final atoms have decayed, the universe will not be empty. Scattered across the cosmic darkness will remain the most mysterious and powerful objects in existence: black holes. Born from the collapse of massive stars or the merging of galaxies, black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. In a cosmos stripped of light and form, black holes will be the final monuments to a once luminous age. Black holes are not merely voids. They possess mass, spin, and a boundary known as the event horizon. Anything that crosses this invisible line is lost forever to the outside universe. Time itself slows at this edge. From our perspective, matter falling into a black hole appears to freeze, caught in an eternal descent. But beyond that horizon, all information vanishes. For many years, scientists believed black holes would endure eternally, immovable anchors in the fabric of space. Then, in the late 20th century, physicist Stephen Hawking introduced a revolutionary idea. By combining the principles of quantum mechanics with general relativity, he showed that black holes are not completely black. They emit radiation, an extremely faint, ghostly glow, now known as Hawking radiation. This emission is not light escaping from inside the black hole, but rather a subtle quantum process occurring just outside the event horizon, where pairs of particles briefly appear and separate. One particle falls inward, the other escapes, stealing away a tiny bit of the black hole's mass. Over vast stretches of time, this process causes the black hole to shrink. Its immense gravity weakens, its temperature rises, and eventually, it begins to evaporate. In its final moments, the black hole blazes briefly with energy before vanishing into nothing. The greatest engines of destruction in the universe are not eternal after all. They, too, must die. This evaporation is astonishingly slow. For a black hole the mass of a star, the process takes more time than the universe has yet existed. But given enough time beyond counting, every black hole will meet this quiet end. One by one, they will disappear, leaving no trace behind. No light, no mass, no gravitational shadow, only a silent void. Their last breath, Hawking radiation, is the universe's final whisper. With the death of black holes, the universe will enter a new and eerie silence. No stars, no galaxies, no atoms or particles, only a faint haze of fading radiation stretched across a cold and infinite emptiness. The grand tapestry of cosmic history, from the fire of the Big Bang to the quiet dissolution of space-time, will come to a close. There will be no more creation, no more collapse, only the memory of what once was, written into the silence itself. And yet, in this stillness lies beauty. Black holes, once thought to be the end of all things, become the final storytellers. Their evaporation marks the closing lines of the universe's last chapter. In the delicate balance between gravity and quantum uncertainty, we find a truth that transcends time, that even the most powerful forces must yield, that even darkness must fade, and that in every silence there is meaning. Every story has an ending, even one as vast and ancient as the universe. As we look into the far future, we find several possible destinies awaiting the cosmos. Each scenario is shaped by the delicate balance between gravity, dark matter, and dark energy. Though different in detail, all paths lead to a profound transformation, an end not only of stars and galaxies, but of space, time, and matter itself. Some conclusions are cold and silent, others are violent and sudden, and one may be lurking beneath the surface of reality right now. The most widely accepted scenario is known as heat death. In this vision, the universe expands forever. Galaxies drift apart, stars burn out, black holes evaporate, and all matter dissolves into radiation and subatomic particles. Over unthinkable timescales, temperature differences vanish, energy spreads thin, and entropy reaches its maximum. There is no more structure, no more possibility of work. The universe becomes a flat, dark, and cold sea, an eternal stillness where nothing more can happen. A very different possibility is the Big Crunch. If gravity were to eventually overpower the expansion driven by dark energy, the universe might reverse course. Galaxies would stop receding and begin to move inward. The cosmos would collapse in on itself, growing hotter and denser until all matter and energy were crushed into a final singularity. Time itself could come to an end, or loop into a new beginning. Some have suggested this could give rise to another Big Bang, a rebirth following the ultimate collapse. More catastrophic still is the Big Rip. If dark energy grows stronger with time, the expansion of the universe would not just continue, it would accelerate beyond all limits. Galaxies would be torn apart, then star systems, then planets, then molecules, then atoms. In the final moments, even space-time would be shredded. The fabric of reality itself would unravel. The universe would not fade or collapse, but be ripped apart, violently, completely, and forever. Then, there is the most unsettling scenario of all: false vacuum decay. According to some quantum theories, the universe may not be in its most stable energy state. Instead, it could exist in a temporary or false vacuum. If a transition to a true vacuum ever occurred, triggered by a quantum fluctuation, it would unleash a bubble of destruction expanding at the speed of light. Everything in its path, including the laws of physics, would be rewritten. There would be no warning, no escape, and no trace of what came before. We do not know which ending, if any, awaits us. Each possibility reveals something about the fragility of existence, the incompleteness of our knowledge, and the strange beauty of a universe that may be finite after all. Whether the cosmos dies in silence, in fire, or in an invisible quantum whisper, one truth remains. The end, like the beginning, is part of the story. And though we may never witness it, we are among the first to imagine it. What came before the Big Bang? It is a question that pierces the very edge of our understanding. For centuries, the beginning of time marked a boundary, a wall beyond which science could not reach. The Big Bang was seen as the origin of everything: space, time, matter, and energy. Yet modern physics has begun to suggest that this singularity might not be the true beginning, but instead a transition. A moment not of absolute birth, but of transformation. And beyond that moment, new ideas emerge, strange, bold, and beautiful. One such idea is the oscillating universe. In this vision, the cosmos is not a one-time event, but a cycle: expansion followed by contraction, then rebirth. A universe like ours may one day collapse in a big crunch, only to bounce back in a new Big Bang. Each cycle wipes away the past and writes a new history. Time stretches forward and backward in a rhythm as old as existence itself. If true, we are just one chapter in an infinite cosmic heartbeat, where universes rise and fall like tides on an eternal sea. Another possibility is the multiverse. According to certain interpretations of quantum theory and cosmic inflation, our universe may be only one bubble in a vast and endless foam of universes. Each one may have different laws of physics, different constants, different histories. Some may be filled with stars and galaxies, others with nothing at all. We live in one bubble among countless others, separated by distances we can never cross and horizons we can never see. The Big Bang, in this view, is just the local spark of a far greater fire. Then, there are theories that connect black holes to creation itself. Some physicists propose that every black hole might contain a new universe inside, a daughter cosmos birthed from the collapse of matter in another. In this picture, our own universe may be the offspring of a black hole in a parent universe. If true, creation is not a singular act, but a branching tree of worlds, each budding from the collapse of another, each carrying the legacy of physics forward like genetic code. Still more speculative is the idea of a quantum bridge, a connection between universes made not through space, but through the fabric of quantum gravity. Wormholes, long imagined in science fiction, might serve as tunnels not only through space and time, but between entire realities. At the Planck scale, where quantum uncertainty reigns, the birth of a universe may be less an explosion and more a phase transition, a shift from one quantum state to another, like ice melting into water. These are not answers, but questions made visible. The truth of what came before the Big Bang may forever elude us. We may be limited not by technology, but by the structure of time itself. And yet, in seeking what lies beyond the beginning, we stretch the reach of human thought into realms that once belonged only to myth. Whether the universe cycles, multiplies, emerges from a black hole, or tunnels across a quantum landscape, one truth remains. The origin is not behind us, it is within us. We are part of the question. We are made of the mystery. When we imagine the universe, we often picture stars, galaxies, and swirling clouds of light, an ocean teeming with cosmic structures. But the deeper we look, the more we discover that much of the cosmos is empty. Vast regions exist where there are no stars, no galaxies, not even a whisper of matter. These are the great voids, immense, silent expanses that span hundreds of millions of light years. They are not gaps between objects. They are structures themselves, cosmic absences that shape the very architecture of the universe. Voids are not simply spaces where matter failed to gather. They are the result of a cosmic dance, gravity pulling matter into dense filaments and clusters, leaving behind cavities that grew larger as the universe expanded. The observable universe resembles a vast sponge, a web-like structure where galaxies are strung along filaments and walls, and the voids form the dark, empty spaces in between. These voids are not rare. They make up the majority of the universe's volume. The cosmos is not crowded. It is mostly hollow. The largest of these voids are almost unimaginably vast. The Bhuta's void, sometimes called the Great Nothing, stretches over 300 million light-years across. It contains far fewer galaxies than expected, just a handful in a space where thousands should reside. Other voids, like the Eridanus supervoid, have been linked to strange anomalies in the cosmic microwave background, leading some to speculate about exotic physics, or even connections to other universes. In these places, reality itself seems thinner, more fragile. Voids are not completely empty. They may contain a sparse dusting of dark matter, lone galaxies wandering in isolation, or streams of gas stretched thin by expansion. But compared to the bustling cosmic web, they are eerie deserts of silence. They challenge our sense of scale, reminding us that emptiness, not substance, defines the vastness of creation. And in their stillness, they may hold clues to the deeper forces that sculpt the universe: dark energy, inflation, and the primordial fluctuations that seeded it all. There is something poetic in these immense absences. In a universe often described through light, voids are the places where light has fled. They are not mistakes or leftovers. They are necessary, like the space between stars in a constellation, or the silence between notes in a song. Without the voids, the structure would collapse, and the beauty would vanish. In the great cosmic emptiness, we find not a lack of meaning, but a different kind of presence, one that speaks not with sound, but with space. At the heart of all things, beneath atoms, beneath space and time, lies uncertainty. Quantum fluctuations, tiny tremors in the vacuum of existence, ripple even in perfect stillness. These fluctuations are not disturbances in something. They are the raw pulse of being itself. From these quantum jitters, entire galaxies may have formed. The fabric of reality, once thought smooth and continuous, now appears to tremble at the smallest scales, giving birth to matter, energy, and even the seeds of the universe. To understand the deepest layers of the cosmos, physics seeks a union between the grand and the granular, between general relativity and quantum mechanics. One such attempt is string theory, a vision where particles are not points, but vibrating strings, each with its own frequency. These strings exist not just in 3 dimensions, but in 10 or 11, curled up so tightly we cannot see them. In this framework, gravity emerges naturally, and all forces become facets of a single, elegant dance. Yet, string theory is not the only path. Another approach is loop quantum gravity, which reimagines space-time itself as granular, a weave of loops, finite and indivisible. In this theory, space is not a smooth backdrop, but a fabric made of quantum threads, constantly shifting, bending, and reconnecting. Time may not flow, but emerge from the relationship between loops. The Big Bang, in this picture, was not a singularity, but a bounce, where an earlier universe collapsed and gave rise to our own. We began our journey with stars and galaxies, crossed the limits of light and time, touched the edges of black holes, and the trembling skin of quantum space. And now, as we drift back from the vast unknown, one truth remains. The universe has no clear edge, no wall, no boundary, no final shore. Its horizon moves with us, shaped not by where the cosmos ends, but by how far our curiosity can reach. In a universe with no border, exploration is infinite, not just out there, but within. We are small, yes, but not insignificant. The atoms that form our hands were born in the hearts of ancient stars. The thoughts behind our eyes are made possible by laws written into the structure of space itself. We are a way for the universe to know itself, not apart from the cosmos, but of it. When we wonder about the beginning of time or the death of light, we are not looking from the outside in. We are the question, and perhaps one day, the answer. In the end, the story of the universe is not only about galaxies and gravity. It is about silence and memory, about becoming and fading, about what it means to exist at all, in a place so vast it humbles the soul. And yet, even in the face of all this enormity, we can find something deeply human, a kind of peace. To be here, for this brief flicker of cosmic time, is a miracle not of scale, but of presence. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.